Okay, so Sama, we will start your BARC full mock interview. Please tell me your three favorite subjects
Heat transfer, fluid mechanics, and basic thermodynamics.
and thermodynamics. Okay, okay, fine. Okay, so I will draw a situation here, a very simple situation. That is, we have a bar here. We have a bar here, right? And this is a constant cross-section bar, and this is your x direction, and this bar is insulated in this direction, right? And
Okay.
now we are applying some heat here. Okay, we are applying, or let us say that at this surface, your temperature is 200 degrees Celsius, and your ambient temperature, T ambient, is equal to 25 degrees Celsius, right? So you have to draw the temperature profile starting from x equal to 0 to, let us say that this bar is of 1 meter. Starting from x equal to 0
Okay.
to x equals to 3 meter. 3 meter. You have to draw the temperature profile. Draw it and show.
Okay.
Yes.
Will be like this.
Like this. Okay. 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 Now consider that you have a second bar, and for the second bar, what you have is the bar is now tapered. Okay. So the
Okay.
cross-sectional area is varying with x. Okay. And
Okay.
obviously it is, I mean, it is having a full length of 1 meter. Now you draw the
Hmm.
temperature profile in the same graph.
Okay. The sides are also diametric for these cases.
Yes, yes, yes. Sides are adiabatic. And at x
Okay.
equal to 0, the temperature is again 200 degrees Celsius. So the boundary conditions are same.
Okay. It will be like this. At start, the slope will be low, and the end point it will increase.
Will the heat transfer increase or decrease?
It will decrease
It will decrease.
because
Why?
overall thermal resistance will increase
Overall
because it
thermal
will have less
resistance,
spaces for transfer heat.
thermal resistance will increase. Okay, okay, okay. So now what will happen if I put a fan here? If I put a fan here and the fan is blowing air in this direction. For this case, for the constant cross section, draw
Okay.
in the same graph.
it will be like this. The temperature at the end will decrease, and the thermal boundary layer after the in air it will decrease.
Okay, so you talked about the thermal boundary layer. So we have here three cases. First case is the constant cross section. Okay, constant cross section. Second case is the tapered one, tapered cross section. Third case is the constant cross section plus fan. Okay, so if I tell this as my delta 1, this as my delta 2, and this as my delta 3. So you already have told me that my delta 3 is less than delta 1, right?
Yes.
So what will happen to delta 2? So you have to,
Delta
yeah, tell me what will happen to
delta
delta
2
2?
will be highest because there will be the highest temperature difference.
Highest temperature difference.
Delta depends on the temperature difference. The more will be the temperature different, more will be the uh, uh, thermal boundary layer difference.
Delta depends on the temperature difference. And on
Yes.
which other, okay, and on which other parameter the delta depends?
It depends on thermal diffusivity, conductivity
Okay,
of
so
the
okay, so if I consider four cases, one is you have a tapered shape, you have a, I mean, these are the three cases. Another case is the tapered cross section plus fan. So I call this as my delta. Now your task is to arrange these deltas, delta 1, 2, 3, 4, in ascending order.
okay.
It will be the increasing order, minimum to maximum. Arrange it.
So delta 3 will be the smallest one. Delta
No,
4 will be
you just write the order, or you just tell me, okay, so delta 3 more than,
less than delta 4. Delta 3 less
yeah,
than delta
less
4.
delta 4, then
Delta 4 less than delta 1.
delta 1, then delta
Delta 1
2.
less than delta. Yes.
Okay, so you are telling that by, okay, okay, tapered cross section. So are you sure? I mean, so can there be any case that my this delta 4 is less than or maybe more than this delta 1? Can this happen or not? Can this happen or not? In any case.
It can happen. It depends upon the
Why,
fan
why?
velocity.
Why it can happen?
Because the fan velocity is small. You can say that fan velocity is low.
Uh,
And so can be the cases that the larger cross section
right.
can have higher heat transfer.
Okay.
It is dominating due to the delta T will be more.
Larger cross section have higher heat transfer. Okay. 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 I understood. Good. Good. Okay. 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 So last thing that now what I am doing is, again, I will just give you three cases. One is your tapered bar with, now what I am doing is, so initially the bars were all horizontal like this. Now I am
Okay.
taking the same bars and just upside down. Okay.
Okay.
So it is a tapered bar upside down. and then I have the cross-sectional bar upside down. Okay. And the other two cases are these two same cases in horizontal that you have already drawn. Right? So take a different TX plane and draw these four cases one by one.
The sides are also insulated in these cases.
Yeah. For every case, sides are insulated and ambient conditions are same.
Okay.
Okay, go step by step. First, you draw for the constant cross section. Draw for the horizontal one and draw for the upside down in the same graph. For the same length, that is starting from x equal to 0 to x equal to 3 meters.
Okay. It will be like this. The one is constant cross-section area in horizontal plane arrangement. The second one is it is in vertical.
Okay.
And the third one is the varying cross-section in horizontal, and fourth one is the varying cross-section in vertical.
So for the second one, the temperature is increasing at the face. Why? I mean, when you are putting the bars in the vertical position, then the temperature profiles are increasing. Why it is happening?
Because the heat transfer will be less.
Why? Why the heat transfer will be less?
In horizontal case, the near the air there will be density, its density will decrease, and it can go upside due to the buoyancy effect, and there will be no resistance in upside direction. But in here the due to heat transfer, the air
Good.
density decrease.
Okay, fine, good. Okay, now we will move to fluid mechanics. Okay. So in fluid mechanics, what did I ask you the previous interview? I should not ask the same thing. Yeah, I think I asked you to Peter tube, right? Okay, so I will not ask you the same thing, right? Okay, so consider that you have a cylinder. Again, we will start with a very simple question. We have a cylinder and we have a pipe here. Okay, and this through this pipe we are filling water with a constant flow rate of Q, and this
Okay.
cylinder is having a maybe the diameter d and also the length is equal to d. Clear?
Mm. Yes.
So first you draw the h versus time graph. Consider that at time t equal to 0, h was equal to 0. You draw this.
Okay. It will be linear.
It will be linear. And what will be the slope?
The slope will be
Or you just tell me the conservation equation.
will be
That will also do.
uh, it, it will be flow rate divided by area.
Flow rate divided by area. Good, good. Okay. Now, in the second case, we are not doing anything magical, but what we are doing is we are now putting the same cylinder, I mean, horizontally.
Mhm.
So we are again doing the same things. One vertical, one horizontal, same scenario. And we are again now, this is my pipe. We are filling it by Q, volumetric rate Q. This is my D, and this is also my D, same cylinder. Now on the same HT graph, you draw the H versus T for the second case. So I will draw
Just a
here the
minute.
first graph. Yeah, yeah, yeah.
Sorry.
Okay. Yeah, yeah, take your time.
Okay. Sorry, sir.
No,
I have
no.
to draw
Okay, okay.
HSST diagram.
Yeah, for the second case. So this is your first case. This is your second case. So first case here, I have also drawn what you have drawn. You have to draw the second case.
Okay. It will be like this. At start, the slope will be maximum and it will be minimum at middle when the tank is half filled. And it will be
So
again maximum at
for the first half the slope is decreasing. Why?
because area is increasing. As area will increase, height increase in height will decrease because the flow rate is constant.
Flow rate is constant. Okay. So now consider that if I put a nozzle here, if I put a nozzle here,
Okay.
okay, then you draw the
Mhm.
H versus T graph. So first of all, you tell me that if I put a nozzle here,
Mhm.
then will the tank fill or it will
It
remain empty
will
because you see the water is coming from here and it is going outside. So what will happen? Will it fill or
it will
because huh? It will fill?
it will depend on
Yeah,
whole of
depend on
cross section area of the hole. If the hole is
cross
big,
section.
then it will
If the
direct.
hole is big, okay,
If the hole is big, then
okay,
the fluid will
okay. So
drain out
you just
directly.
consider that your D is 1 meter. Your D is 1 meter. Okay. So if I take this as my zero point 0.5, 0.25 meter, what will happen? Will it fill or will it remain empty?
Again, it will also depend on the flow rate coming in the cylinder.
Flow rate you consider it is maybe 50 meter cube per second.
Meter per second. Okay.
Okay, if I just give you the scenario, if I just give you the scenario that the hole is uh, okay, you just uh, okay, the scenario is exactly correct. Okay, you just draw it. Okay, fine, fine. Sorry to confuse you. Just draw it, or you just tell me first that will it fill it or not? Will it fill or not? What do you
Just a
think?
minute.
Yeah, yeah. Take your time. Okay, if the nozzle is very small,
It
then
should
if
fill.
this nozzle is very small,
Mhm.
maybe it is just of 5 centimeter diameter.
Should fill.
Hmm? It will fill.
It will fill.
It will fill. Why? Because you see that here water is coming and it is going outside, so it should remain empty, right?
But the flow coming out of the that hole will be not much as the flow coming onto the tank.
Now you see at steady state, you understand steady
At
state?
steady state.
Yeah. So at steady state, flow from this end should be equal to flow from this end.
Yes, at steady state also, but we are considering the tank is filling, so it is the not the
Okay,
case
so
of
you are
steady state.
considering that it will reach a steady state height, and the steady state
Will
height is not zero. You are considering that.
the steady state height we need to calculate this.
Yes, that means you are saying that it will be more than zero.
Yes, if steady state is coming, then it should be more than zero.
Okay, so you consider that the steady state is coming. I mean, if it is more than zero, you are telling that
Okay,
maybe this will be my steady state height. You draw the h versus t curve on the on the same curve. This h versus t curve. You draw a curve
okay.
and you draw the straight line, and then you compare the two situations.
it will be like this. This is the when we are considering there is a hole. After
The
some
slope
time, it
will,
will be constant height at the time when the steady state is achieved.
why the slope is decreasing?
Because when the flow coming is constant, but the flow uh, going out from the hole will be varying as the height will increase. As the height will increase, the velocity of the flow will increase as per equation root 2gh. When the height increase, the flow of coming out from the tank will increase. So ultimate flow will reduce as per time. The Q in minus Q out
Okay,
will decrease
okay,
as time
okay,
as height
okay,
increases.
okay. So now the final thing. Now what I am doing is I am just putting this cylinder with this pipe in a box. Maybe I should draw it
Okay.
with this color in a box. So in the previous two situations, the ambient pressure was atmospheric. Now what I am doing is I am sucking out air from it. I am sucking out air from it.
Okay.
Okay. So if I suck out,
Okay.
if I keep sucking out air from it, then you draw the H versus T curve. Okay. By the way, one more thing, that the
Hmm.
discharge, this discharge is happening at atmosphere, right? This
Discharge is
discharge is
happening at atmosphere.
right.
So from where the air is sucking out? In the cylinder?
No, no, no. This
From
cylinder
the
is
cylinder?
kept in a box. This cylinder is kept in a box, and
Okay.
in the wall of the box there is a small, maybe a small pipe or a small nozzle, and I have connected a
Okay.
suction pump with this, and this suction pump is sucking out air.
We are assuming that flow Q coming into the tank is constant.
Yeah, yeah, yeah. Q is constant. You, okay, one thing, you just tell me the approach. I mean, what will you do to analyze
Well,
this?
sorry, what we
You
just
just tell
you
me,
asked.
you just tell me the approach, that what will you do to analyze this situation?
So there is no difference because the flow coming into the cell tank is same, and the flow coming out to the tank, the inside tank, is will be also the same. So the same graph will look
Okay, okay,
like the
okay,
previous graph.
okay, okay. So the final task for you, draw the famous Rankine cycle. NTS type. Okay, okay, fine. Now tell me that, I mean, explain each of the four processes.
Okay. We
What
are
is one to
considering
two?
ideal reversible Rankine cycle
Ideal,
in
yeah,
which
true. 1 to 2
from 1
is,
to 2 will pumping the liquid to water.
is it
After that, we
isentropic or
will
Is it isentropic
Sorry.
or
Yeah, yes, isentropic. Adiabatic
so
isentropic pressure.
isentropic?
After that, we will, isobarically constant pressure, we will provide it. This is
Acha,
preheating,
acha.
this is the
Okay,
boiling, and this is superheating
okay.
at constant
Then,
pressure. After that,
then
we
three
will
to four.
isentropically expand in turbine,
Mm-hmm.
and this
Then,
is constant pressure condensing. We will condense from vapor to liquid.
okay, okay, okay. So you tell me that how do we condense generally? How do we condense the steam? Generally,
We
what do
will
we do?
condense it. Yes, we will condense it at subatmospheric pressure in heat
No,
exchanger
no.
by
Yes, yes.
other
Okay.
water.
Tell. Heat exchanger.
Uh, yes, in heat exchanger, its pressure will be approximately 7 to 10 or 15 kilopascal, and the temperature will be approximately 45 to 50 degrees centigrade. And we will have a water reservoir which will be passed through the heat exchanger. In one circuit, we will pass the steam, and the other circuit we will pass to atmospheric temperature water,
Okay,
which
okay,
will have the temperature 25
okay,
degrees centigrade,
okay. Fine.
which will.
So you
Mm,
tell me, if instead of having this very expensive heat exchanger, if I just put the hot steam in a large lake and I take the water from that
okay.
lake, okay. So I am just replacing the condenser by a large lake. I am just putting the hot steam
Okay.
in that lake, and I am taking the water into the pump. Okay.
Okay.
So will it work? Will the Rankine cycle work?
We need, if the pump inlet pressure is atmospheric pressure, then it's okay. If the pressure is subatmospheric pressure, though we need to first depressurize the water, and before that we need to uh, do water treatment, because the water has some impurities and which need to be
What will
uh,
happen if I
filtered out.
don't depressurize the water? First of all, I cannot depressurize a large lake, right? Because it is a large lake.
Yes, yes,
So what will
yes.
happen if I don't depressurize the water? So my first question is
So,
that will the cycle work or not? Yes or no? Answer is this.
yes,
So it will
yes,
work.
it will
The
work.
the
Yes.
the cycle. Okay. Okay.
Okay.
Okay. Fine.
And
Fine.
its
Fine.
efficiency will decrease.
Efficiency will decrease. Okay. Okay. Fine. Your interview is over. Now let me give you the feedback. So honestly,
Okay.
for the heat transfer, your performance was 100% good, very good. Okay, you have uh, tackled all the scenarios very well, and mostly in BRC interviews, they are very interested with the thermal boundary layer thickness, and they will make you draw in the temperature profile. So what you should at this level, you should prepare with the non-idealistic case. For example, I have asked you that the two sides were insulated. Now you prepare by yourself that if half of the length was insulated and half of the length was not insulated, then
Okay.
then what will happen to the temperature profile? Because see, these type of cases, you cannot just draw it by some mathematical equation. You need some very good engineering sense to draw it. Okay, because
Yes.
they will tell you that don't write any equation and draw it. So you now think by yourself some practical situations which we cannot solve analytically. Then you try to draw the temperature profile. Okay, this will be your
Yes.
next goal. Now for the fluid mechanics, you have almost done it very good. I have asked the same question so many students, but they actually were not able to draw this curve. but you have drawn it. That's why I was, just the leveling up the question. But the final question, you think that the answer was actually not correct, you think. And I will also, give you the hint that you are telling that this will the water will go out. And how do you calculate the flow rate? By applying the Bernoulli's equation. And in the Bernoulli's
Yes.
equation, there is one pressure head. So when I suck out
Yes.
this air, that pressure head will change. So that outside flow rate will also change according to that change of pressure. Okay. So at the first case, so for the first case, the outside the outside uh, discharge pressure was ambient, and also in this region was also the ambient atmospheric pressure. But in the second case, the outside is at the ambient pressure, but now this inside pressure is subatmospheric. So that will affect
But
his discharge rate.
the pressure inside the tank, sky blue tank, the
Hmm.
pressure inside will also decrease.
Pressure inside will, yes, pressure inside will, there will be a pressure jump, obviously. Okay. You think over it because we don't have much time.
Okay.
Okay. Okay.
Okay.
And the thermodynamics question was also 100% right. Okay. So in this interview, I
Okay.
actually put more focus on fluid mechanics and heat transfer, and I put less focus on
Yes.
thermodynamics because you answered well in the thermodynamics interview for the previous interview. You just think about this one. Okay. Maybe I
Okay.
will mail you, and if you got any kind of confusion, regarding this question, then I will also, help you through the mail. Okay.